Alright, so welcome back to the OneClass channel. Again, my name is Joey. I'm going to be your chemistry teacher for this session. So just a little bit about OneClass if you're tuning in for the first time. At OneClass, what we're doing is we're providing some videos and live streams, and basically resources for frequently asked questions in subjects such as mathematics and in chemistry. Both are offered in basically the high school level and also in the university and college level. So we've been curating these questions for some time now, and although teachers here at OneClass, including myself, what we're doing is we're verifying these solutions so that you have the best solutions moving forward to maybe any assignments or tests or any upcoming courses that you might face. So what we're doing here at OneClass is we're providing you with the best solutions, and we're going to teach you the concepts through verifying the solutions for you so that you have better tools moving forward in your classes. So my name is Joey. I'm currently an Ontario secondary school teacher in Ontario, and what I'm doing here at OneClass is I'm specializing in subjects such as in math and chemistry. So if you're tuning in for the first time, thank you so much for watching. What we have here is a set of about 10 questions for us to kind of go through, and these questions are going to basically be in the high school level, so anywhere from basically grade 10 all the way up to grade 12, and the next stream after we're going to do some university level questions. So without further ado, let's get started on these types of problems here. Okay, so I guess we have three kind of questions in total here. But I'm just going to look at the first one here, just because they only verified the first one. So they didn't look at these two as well. So I'm only just going to look at the first one here. And this is question 1 for the day, even though it says question 9. Make sure my pen works here. There we go. So it says it's asking us, what is the strongest type of intermolecular force present in NH2CH3? So we have NH2CH3, and we want the strongest intermolecular force, right? We want the strongest intermolecular force. So with these problems, what I like to do is I like to draw the kind of structural diagram of the chemical compound here. So what we have here is, so we have a carbon here, and it's bonded to, we're taking the least electronegative atom here, which is carbon. So carbon's gonna be in the middle here. It's gonna be bonded to 3 hydrogens, right? So I have 1, 2, and 3. And then it's gonna be bonded to this nitrogen here, which is also bonded to 2 hydrogens here. So I have an N here, and then it's going to be bonded to, you can write this as H, and this is H here. And this here is our chemical compound for NH2CH3. It's asking us which intermolecular force is present. So let's look at the first one here. It's ion dipole. Is ion dipole, does that exist here? And in this case, we do not have an ion dipole, right? We don't have an ion here. It's not being dissociated into water or anything, so we don't actually get our ions here. And as you can see here, we have a covalent compound. So it's not very, very likely to dissociate into some type of solution such as water. So we don't have ion dipole, so that's not the correct answer here. And we're looking for, again, the strongest intermolecular force, right? So I'm going to list out basically all the intermolecular forces first, and then we will rank them. So we don't have ion dipole, so number 1 is wrong. I'm assuming number 2 is London dispersion. I think they just misspelled it here, but we do have London dispersion, right? So we have, right here, London dispersion. And we do have this because it's an aliphatic chain, right? We have carbon, bonded hydrogen, bonded nitrogen, bonded hydrogen. Basically, it's just these weak electrostatic forces that exist in a compound. And again, with London dispersion, the bigger the compound, the more London dispersion forces that they will have here, or the stronger the forces might be. Next one, we have dipole-dipole. So we have London dispersion, and we also have dipole-dipole. So how we have that here is because I know that my carbon here and my nitrogen here is going to draw out electron density, right? So again, I know that this carbon here is partial positive, and this nitrogen is partial negative, because this one, again, I have a lone pair. You can think of this on nitrogen here, and it's pulling away electron density. So this is here is partial negative, and this carbon here is partial positive. So the dipole is shifting here. You can think of the dipole here as it's shifting towards the left-hand side here, because it's pulling electron density away from this carbon here. So in this case, we do have dipole-dipole, and this is stronger than the London dispersion, right? So dipole-dipole is currently our strongest one. And then finally, do we have hydrogen bonding? Hydrogen bonding? And the answer is yes, we do have hydrogen bonding. We have, remember, hydrogen bonding only exists with 3 elements. It's hydrogen bonded to either. So it's obviously, I need a hydrogen and hydrogen bonding. Hydrogen is bonded to N, O, or F. And as you can see here, we have these 2 bonds, right? This bond here. This is again partial negative. This is partial positive. This is partial positive. And as you can see, these 2 bonds here, these two guys here, are hydrogen bonding. So these guys here, let me just highlight them in blue instead of box them. So these guys here, or yeah, I won't draw the partial. So these guys here bonded to the nitrogen here are examples of hydrogen bonding, because again I have, and they're very, very strong. They're actually the strongest intramolecular force that exists here, besides the ionic forces. So in this case here, we do have hydrogen bonding, because again we have N bonded to H here, and again it's drawing away partial. It's pulling electron density away as well, right? So the hydrogen here is partial positive, and it's pulling away electron density. So in this case here, we do have hydrogen bonding, and it actually is the strongest type of intermolecular force within the 3. And if I were to rank them, hydrogen bonding is the strongest one, and then it's dipole-dipole, and then it's London dispersion. So London dispersion is the weakest one. Dipole-dipole is the second weakest, and hydrogen bonding is obviously the strongest intermolecular force. So in this case, the answer here is hydrogen bonding. And let's look at the solution here. And answer 9 here, it says hydrogen bonding, which is correct. So it says, since hydrogen and nitrogen atoms are present in the compound, it is capable of forming hydrogen bonds with other molecules. London dispersion forces are also present, but the hydrogen bonding is the strongest. So this here solution is correct. If we had another NH2 molecule, NH2CH3 molecule, like if I were to draw another one out, you can see that you can actually have, again, it is also attracted to itself, right? So let me draw this out here. And again, we have this here is partial positive. Sorry, partial positive. This one's here is partial positive. Let's go here is partial negative. We have bonds that are from this nitrogen to this hydrogen as well, right? These guys are attracted to each other, and then these guys, this nitrogen and this hydrogen will also be attracted together. So this here is also our H bonding as well. So again, so all of these guys here are again make up the strongest intermolecular force. So this here is correct. Again, this person didn't verify this or this solution here as well. So I'm not gonna say this solution is. It's more so the solution is incomplete, because this person was only asking question 9. So they didn't say do these 2 problems as well. So in this case, I'm going to say solution is correct, because I'm assuming they're only asking 1 question. Good analysis here. Strongest to weakest. And then I'm going to just expand on their answer here. Intermolecular forces. So it's we have hydrogen bonding first. And then we have dipole-dipole. And finally, London dispersion. So the solution here is correct. Okay, number 2 is asking us, I have some type of chemical equation, and it says a conjugate acid-base pair in the reaction shown above is, and then it gives us, it's a multiple choice answer. So let me write this down here. I have CH3, NH3, so methylamine, plus HCl is going to be in equilibrium with CH3, NH3 plus Cl minus. It's asking us which one is the conjugate acid base pair in the reaction shown above. So let me write this down here. So I want the conjugate acid base pair. Okay. So how do I find the conjugate acid base pair? Well, I'll do this in red. Actually, I'll do this in blue. Blue for acid and red for base here. So I'm looking at these compounds here. Basically, I want to look at, I'm looking at kind of pairs of compounds. So if I were to break this up, I kind of have two parts, right? So I have this part here, which is the methylamine, and it gets pronated to make this. I forgot the positive charge here. Sorry. This here is a positive, and here is positive. And here is, I have a methylamine that's pronated, right? So I have a positive charge here, and then I'm looking at HCl here, and then Cl minus, right? So again, I'm looking at these guys here. Specifically, let's look at methylamine first. So I have CH3 and H2, and then it's going to react to form, or it's in equilibrium with CH3 and H3 plus. And as you can see here, this guy here is gaining or losing a proton, and we can look at this through using Bronsted-Lowry theory, where it states that Bronsted-Lowry let me write up Bronsted-Lowry theory. Acid or Bronsted base states that if we were to get rid of a hydrogen, they are you can think of it as, if I'm losing a hydrogen here, it becomes an acid. It's an acid, right? If an electron donating, I'm an acid, and hydrogen donating, I would be an acid, and hydrogen accepting, I would be a base, right? So in this case here, I have Bronsted-Lowry acid would be, you can say, donating H, and then Bronsted-Lowry, use these quotes here for a base, is base here would be accepting a hydrogen proton, right? And this here is H plus here. So I'm looking at these guys here, and as you can see, which one's donating my hydrogen? It's definitely not these two guys, right? I have NH2 and then NH3 plus. It's not donating a hydrogen. I'm actually accepting one. I gained a hydrogen if I went to towards the right hand side, right? So it has to be my HCl. HCl, as you can see, HCl becomes Cl minus here. I'm losing a hydrogen, so it's donating a hydrogen here, right? So as you can see here, this guy here would be my acid. HCl here is my acid, which means Cl minus is my conjugate base, right? So I can say this here is one of my two conjugate acid and conjugate base pairs. So this, I would write here conjugate base, or Cb here, conjugate base here. And then, which means if I have an acid here, therefore this one must be a base, right? So this here is a base, and this one here would be my Ca, or my conjugate acid. And these two are my conjugate acid base pairs. And all I'm going to have to do is look at these guys here, right? I'm just looking at which one fits the criteria. And this one is not correct. This one's also not correct. This one's also not correct. This one's not correct. And E here has to be my final answer, right? HCl is my acid, and then conjugate base would be my Cl minus here. So we say E here is the correct answer. So solution here is correct. So all you need to know about this question is basically testing Bronsted-Lowry theory, where basically it says if a compound is donating a hydrogen, it is an acid. If it's accepting a hydrogen, it's a base, right? In this case, HCl is donating a hydrogen to make Cl minus, right? I'm giving this away to this CH3NH3, right? So therefore, this here is acid, and this one here would be the conjugate base, right? And then finally, with this methylamine here, this one would have to be the base because I am accepting, right? If I'm going towards the right hand side, I'm accepting a hydrogen, right? NH2 becomes NH3 plus. So this here would be my base, which means this guy here would be my conjugate acid. So solution is correct. Great analysis here. Let's look at number 3. So number 3 is asking us how many valence electrons does zinc have? So valence electrons of zinc. And what I'm going to do is I'm going to pull up a periodic table because we're going to need to know our periodic table for this solution here. And we want to know where zinc is, right? So we want the valence electrons of zinc. So zinc here is number 30 here. So zinc here is, you can think of this as group 12, and this here is group 12, and then number 30 here. So we care about what are the valence electrons does zinc have. So if we were to kind of approach this question using our Bohr-Rutherford diagram, you're going to realize that this Bohr-Rutherford diagram is going to fail for zinc, because zinc here is going to be zinc here is a multivalent compound, right? You're going to see that zinc here has much more, has basically adopts different valence electrons depending on which oxidation state it's at. So if we were to write the Bohr-Rutherford diagram, you're going to realize for group 12, you're not going to really get a lot of, it's going to be basically not valid for this problem here. Recall that Bohr-Rutherford is kind of it's limited basically to the first kind of 2 rows of the periodic table, and then after the 3rd row it completely becomes invalid, basically due to the creation of SBDF orbitals, and how 3D you have D, or the D block and the F block as well, that totally do not follow the Bohr-Rutherford theory. In this case, zinc here is in the 3D10 block, right? So basically we can't use a Bohr-Rutherford, so we need to use the electron configuration diagram here. So right down here, we need to know the electron configuration of zinc. How do we know that? Well, we know Zn is our zinc here, and then we're going to write out the electron configuration. So we can see that zinc here lies here, so it has to possess hydrogen and helium, so this is 1s2. So remember, it's sp_df, right? And basically listing it from the beginning, so this is 1s2. We have 2s2 is our next block, contains those 2 electrons, 2s2. And then I have this is the 2p6, right? Again, the group 18 is cut off here, but I know that that would also contain the 2p6 electrons. I have 3s2 here for these 2 electrons. I'm going to have 3p6 for these electrons. Remember, zinc is here, right? So it's going to contain 3p6 here. I'm going to have 4s2 for these 2 electrons. And then finally, I have this block, right? And zinc lies at the end of group 12. So this here would be my 3d10 block. So this is the D block. And as you can see, you can very, very much see here that Bohr-Rutherford fails here, because again, I have 10 electrons in an orbital, right? Or in Bohr-Rutherford states that it's like a maximum of 2 and then 8 and then 18 or something like that, or 8, another 8, I don't know. Either way, the Bohr-Rutherford diagram fails here. So in this case here, I'm looking at zinc here, and I'm looking at what are the valence electrons? Well, I'm looking at basically the highest principal quantum number, which here is 4. Remember here, and the principal quantum number of zinc here is n equals 4, right? Because I'm looking at the biggest number, or the greatest number here, 4. And then valence electron is whatever electrons exist in that orbital. So 4s2, which means therefore I have 2 s electrons, so therefore my valence electrons for zinc, I have 2 valence electrons for zinc here, because my principal quantum number is 4, and that's going to be the highest energy level for zinc, and in that energy level I have 2 electrons here. So I have 2 valence electrons for zinc is my answer here. And as you can see, they also wrote here, right? Therefore, zinc has 2 valence electrons, because they also wrote out the electron configuration, and the highest principal energy level is 4. Like I said, n here equals 4, and I have 2 s electrons there. So this solution here is correct. Solution is correct. Good analysis. Okay, number 4. Number 4 is asking, what is the atomic number of the element located in group 16, period 2 of the periodic table? Okay, so let's go number 4. I want the atomic number of the element located in group 16, period 2 of the periodic table. We know that already. So we're looking at the atomic number of the element located in group 16, period 2. So group 16, as you can see, these guys here are all groups, right? So I have 1 all the way through to 18 here. and I'm looking at 1 to 16, right? So again, I'm looking at group 16 here. So specifically this column, the chalcogen column, and I'm looking at here period 2. So remember, groups here are the vertical columns, periods are the horizontal rows, right? So in this case, I want 1, 2, and then I want all the way to 16 here. So 16 is here, and then period 2 here is this guy here, which means it's pointing to this element here, which is oxygen. So the atomic number for oxygen here is number 8, right? So again, the answer here is, what is the atomic number? Well, the atomic number, therefore, the atomic number equals 8, and it refers to the element is oxygen. So that is here is our answer. As you can see, the answer here is group 16. Oxygen is group 16 period 2, and it has an atomic number of 8 here. So solution here is correct. Good analysis. Okay, number 5 here. Got thrown off by the number here. Number 5 here saying, what are functionalized hydrocarbons? Cite an example of a functionalized hydrocarbon. So, functionalized hydrocarbon, and then I want an example. So let me show you what a non-functionalized hydrocarbon would be first. So if I were to do a structural diagram, it would look something like the simplest non-functionalized hydrocarbon would look something like this. It would be methane. So you can think of this as CH4. It's a really bad diagram here. So I have CH4, right? This guy here is methane. And this is CH4. So again, these guys here only contain carbons and hydrogens, right? So this here is non-functionalized. And you can think of this as it does not possess a functional group. So it only contains C and H. So in this case here, this is non-functionalized. And if I want to look at a functionalized hydrocarbon and give an example, I would basically throw a functional group on top of this guy here. So maybe I'll do an aldehyde or something like that. So I would have, following this structure, what if I had a aldehyde here? So I have a double bond O here. This here would be bond H, and this here is bond H as well. So I have this here is methanaldehyde, or you can say it's formaldehyde for its common name, but I'm going to write down the IUPAC for you as well. So methanaldehyde, or people will just write it as formaldehyde. And this here, as you can see, is CH2O, right? So this here is a functionalized group, right? This here, I have some sort of it's functionalized because I have a functional group, right? And as you can see, the C double bond O here makes it a functional group, right? I have something that's not only containing carbon and hydrogen, right? I have, in this case here, I have an oxygen, right? So this guy here is my functional group. I have an carbonyl, you can say a carbonyl functional group. And it doesn't have to be a carbonyl. It could have been like an amine or a amide or a carboxylic acid or a alcohol or something like that. It depends on what the functional group is. And these guys specifically give them the properties of what a functionalized hydrocarbon is. So for example, in this one here, I have, again, a dipole-dipole. I have a dipole-dipole force that's working inside in the compound here. It's the most predominant intermolecular force, right? So in this case here, it changes the properties of the hydrocarbon. So let's see. For example, alcohol. The functionalized hydrocarbons are the hydrocarbons attached to the functional or a functional group is incorporated into the hydrocarbon. For example, methanol is a liquid, whereas methane is a gas. Okay, so I guess they're using methane as the non-functionalized and methanol as their functionalized group. So I think their answer is the solution here is incomplete because it doesn't really like, it says, for example, alcohol, and then it cuts off, right? So I think it might be a copy and paste issue or something like that. So I'll just say solution here is incomplete. Methanol is a functionalized hydrocarbon, whereas methane is a non-functionalized hydrocarbon. And methanol contains a hydroxyl group. Remember, I used formaldehyde as an example. They're using methanol here, so I'm just going to go with this one. Methanol contains a hydroxyl group, which gives it different properties because it contains a OH group. Yeah, there we go. So I'll say solution here is just incomplete because they didn't really fill this out. So I'm going to say solution here is incorrect just for the sake of this. Okay, number 6 is asking us, summarize the history of the atomic idea. How was Dalton able to convince others to accept an idea that has been controversial for 2,000 years? So this one here is a very general question, and it's more so asking us the idea, the history behind the atomic, the atom, basically. So again, what this is again, when we go back to like the super early days with like the Greeks and whatnot, they thought that the atom here was the only thing that they've discovered is basically the atom is the smallest unit, right? But they didn't have they didn't know what we know now, right? Well, so a brief history of this is, you can think of it as the Greeks here, or sorry, refresh this here. So let me zoom in here. So I have the Greeks here, or the basically ancient Greeks here. They thought that the atom was the smallest compound, right? Equals smallest particles. And they didn't really call it the atom. They just knew that it was the smallest particle. And we actually give them the word atom based off the Greeks, because atom is, I think the prefix here means small, right? And after that, Dalton here, the next kind of person to kind of break this theory was Dalton. And Dalton kind of what his kind of summarization of the atomic theory was that Dalton stated that the atoms are the smallest particles. So they restated this here, but he also came up with this idea of the he built on this idea of the law of conservation of mass and the law of multiple proportions. So when we're thinking of this problem here, we're thinking of, okay, so if I had, it's easier with an example. So I'm going to write down here a law of multiple proportions. And then he also, with Lavoisier, he also came up with the law of conservation of mass as well. But let's look at specifically the law of multiple proportions here. And what that is that when basically two different elements combine to form different compounds, like say here, the masses of one element with the constant mass of another element in different compounds are always related to each other here. So let's think of this problem here. If I have, again, hydrogen gas plus oxygen gas is going to give me water. So currently here on the left side, on the reactant side, I have two hydrogens, right? I have two hydrogens here and two oxygens here. And this side I have two hydrogens, but I only have one oxygen here. So in this case, this equation here does not obey my law of multiple proportions, because I have, again, the masses do not add up, right? I have two hydrogens and two oxygens. I have two hydrogens and one oxygen on this side here, right? So again, it's not going to add up. So therefore, what I need to do is I'm going to have to come up with a proportion between these two sides, right? And we know this as balancing chemical equations, right? So I would put a coefficient here of 2, which would change these values to, again, I have 4 hydrogens here and 2 oxygens here. And then on this side, if I want to have 4 here, I want to also put a 2 here to balance this out. Now, what I have here is a balanced chemical equation, and this here obeys the law of multiple proportions, and it actually also obeys the law of conservation of mass, because again, mass here is neither created nor destroyed, it's simply transferred, and what we have here is law of multiple proportions, right? So the mass here of the reactants are the same as the mass of our products here. So again, it's only again, when two different elements combine to form different compounds, such as water, the masses of one element with a constant mass are always the same, are related to each other as a whole number. So in this case here, this is a 2, and this here is a 2 as well. So this solution here is correct. It's kind of incomplete, but I'm just going to give it to them here. Solution is correct. Dalton proposed the idea of the law of multiple proportions, and with Lavoisier also contributed to the law of conservation of mass. Okay, let's look at number 7. It says here, a solution of household bleach contains 5.25% sodium hypochlorite by mass. Assuming that the density of bleach is the same as water, calculate the volume of household bleach that should be diluted with water to make 500 milliliters of a pH 10.26 solution. This is number 7. Yes, number 7 here. So again, I'm given a solution of household bleach, right? It contains 5.25, and this is a mass percent of NaOHCl, right, by mass. So what we're gonna have to do first is, this here is a correct solution, right? What we're gonna do here is we're going to assume 100 grams, and that when we assume 100 grams of something, it basically means our percent here equals our simply grams here. So I'm gonna say assume 100 grams of, and this here is household bleach, right? Bleach here. So therefore we can say that 5.25 this is NaOCl equals 5.25 grams of NaOCl. So now we have something in grams, which is great. And what we need to do now is we need to find some type of concentration for us, because we know here NaOCl here, sodium hypochlorite here, is in this case here it'd be, I believe, a weak base. So what we need to do here is we need to find a concentration for this, so we can start using because we know it's going to be in equilibrium. So in this case here, I have massive grams. I'm gonna have to find the moles of this guy here. So I know that moles, the N of NaOCl equals our mass of NaOCl divided by the molar mass of NaOCl. This here is 5.25 grams divided by our molar mass here of our NaOCl. So Na here is, I'm finding the molar mass here. Na is 22.99. This is 22.99 plus O here, oxygen here has an atomic mass of 15.99. 999, and chlorine is 35.45 here. Oh, sorry, 35.45. And then this here, I'm going to just plug this into my calculator. This will give me the moles of our sodium hypochlorite. So I have 5.25. I'm going to divide that by the sum of 22.99 plus 15.999. Plus 15.999 plus 35.45 here. Oh, 35.45, and I'm going to get a value of, this is 0.071 here. This is moles of NaOCl. So now we're given the moles of NaOCl. What we need to do is find the concentration, right? Because I have moles here, I want to find the concentration. So if I were to figure this out, what I'm going to have to do is I'm going to have to divide it by the volume, right? So I can figure out the concentration. It also says here, assuming that the density of bleach is the same as water, calculate the volume in moles, or sorry, in milliliters here. So I'm gonna have to do some type of conversion here because I have to actually be in milliliters. So maybe I would save that step to maybe the end here. But what I have here so far is that I have here 0.071. And if I assumed that I have, again, a 1 liter of our volume here, it's going to equal our, this is going to equal 0.71 moles of our solution here, of our which is our concentration here. So let me, I'm just gonna look at the solution here, and it says here that 1 gram, which is the 1 gram per milliliter, which is the density of water, times 1,000 milliliters times 0.0525, which is the percent of hypochlorite, multiplied by 1 divided by 74.44 here. And again, I'm assuming 74.44 is the molar mass of sodium hypochlorite. Yes, it is. So what they're doing here is they're taking they're trying to look at what is the concentration for 5.25% bleach. So they simply just dividing this number by 1,000, right? By 1,000, or by 1 liter here, which is simply just also they're multiplying this by 100 because they're going to convert the density. So the density here times 1,000 milliliters multiplied by our percentage, which is 0.525, and multiplied by the molar mass here. So we're assuming here 1 gram of our bleach here, and therefore we get a 0.71 moles for our 5.25 or 5.25% bleach. So let me write this down here. And I'm going to get, so basically I'm multiplying the density by 1,000 milliliters to convert that into grams. So I'm multiplying that by 1,000 milliliters, and I'm going to multiply that by our percentage, right? So this is 0.525, 0.0525 multiplied by our, I'm assuming 1 gram, obviously, of our bleach. So I would have 1 gram over our molar mass here, which is 74.44 grams per mole. And this will give me here, again, grams and milliliters cancel out here. The grams here cancel out. So I would be given here moles per liter. So let me do this again. Let me just verify this solution here. So 1 times 1,000 times 0.525 times 1 over 74.44. This will give me a value of indeed 0.71, right? So this here would equal 0.71 moles for basically 5.25% bleach here. So now what we have here is we have, again, our moles of our NaOCl, and we have our concentration for this guy here as well. So what we can do is now we can write out our chemical equation, right? So we know here we have sodium hypochlorite. So let me do this in blue now for change of place. I have NaOCl. It's going to be in equilibrium with, well, it's actually first going to dissociate because this here is an ionic compound, right? So it's going to dissociate into basically Na plus OCl minus. And then what this guy here, or let me write ClO minus for you, actually. That'd be easier because the negative is technically on the oxygen here. And then what this guy, ClO minus here, is going to react with the water to form, I have HClO plus OH minus here. And again, this here is our kind of equilibrium equation here, right? Because again, this is going to first dissociate, and the ClO minus is going to react in solution with water, right? And again, these are all in the aqueous state here. So I believe they flipped it actually. So this is supposed to dissociate, so it's actually only one way here, and this here is our equilibrium constant here. So they definitely flipped this. That's okay here. Let's see. So now we're given our pH, right? So we have to actually work backwards to solve for a volume here. So if I have my pH here, what I want to do is I want to, given here I have a what I could do first is I could point out my conjugate acid base pairs, right? So as you can see, I have water here, and I know OH here is the base here, right? So therefore this guy has to be the acid here. So water in this case acts as acid, and this here, hydroxide is obviously our conjugate base. Again, I am accepting a, I'm donating a hydrogen here, right? Yes, I am give me a second here. So let me scroll back here because I kind of lost track of my thing here, and let me see what I wrote here. Yes, so Bronsted-Lowry theory again. Donating H here would be our acid. Right? If I'm donating a hydrogen here, I would get an acid. If I'm accepting a hydrogen, it would be a base, right? So again, here HCl here is my acid. I'm donating a hydrogen, and this here would be our conjugate base here. So it would have to. So for this question here, I'm donating a hydrogen here. This guy is being donated to this guy here. So this guy here has to be my acid. So again, this here is my acid. This here is my conjugate base, which means this blue one here, this one would have to be my base, right? And this base is here. And again, this here is accepting my my hydrogen here. So this here is our Ca, or conjugate acid. So if I'm looking at ClO minus here, I'm looking at I'm given the pH here, right? And again, this here is a base. So I'm actually going to write a Kb expression here. So Kb here is going to equal, I believe this is already balanced. I don't have to touch anything here. So this here is the concentration of ClO times the concentration of hydroxide divided by the concentration of our hypochlorite ion here. And we don't know our Kb, and we actually have to find our Kb through our pH here. So given our pH here is 10.26, what we're going to have to do is first solve for our pOH, right? So we know that pH plus pOH equals 14. And we know that pH here is 10.26 plus pOH here is going to equal 14. So therefore, if I subtract both sides by 10.26, I'm going to get pOH here will equal, I believe this is 3.74. And 3.74 here is our power of hydrogen here. And what we have to do is, I also know that our pOH here equals negative log of our hydroxide ion, right? And basically, if we have our hydroxide ion here, we can solve for our Kb here. So given this, I can write pOH here is 3.74 equals negative log of our hydroxide ion, which means our hydroxide ion is simply just 10 to the negative 3.74, which would equal, this here is 1.82 times 10 to the negative 4. That's exactly what they got as well, which is great. 10 to the negative 4. And this here will be our, this here is our concentration of a hydroxide, right? So this is going to be this guy here. So as you can see, this here is, this is some good work here. So they have the in equilibrium here, which is great. And then what they're doing here is they're finding the Kb constant as well, right? So this here is we can actually solve for a Kb here. So let me plug this in to our equation here. So this here would be I'm not sure if we're actually given the Kb for the question, but in this case here, I'm pretty sure we're given the Ka for this for our acid dissociation constant for HClO, and this here was 3.0 times 10 to the negative 8 here. They usually give you a list of Kas when you're doing these problems, just because you need to know the Ka here. So so let's see. So if I didn't want to search it up, but again, they wrote here, this is 3.0 times 10 to the negative 8, which is the acid dissociation constant. So this is the Ka. And what they're doing is they're organizing this to find the Kb, right? So this here is 3.3 times 10 to the negative 7, which is this Kb over here. And now they have, and what we can do is we can figure out our concentrations here, right? So this here is 3.3 times 10 to the negative 7. And we know that our both our x's here are 1.82 times 10 to the negative 4, right? So this here, these concentrations are obviously the same, and we just don't know this guy here. So what we can do is we can just use simple algebra here, right? So we can say that this here is 1.82 times 10 to the negative 4 squared. 10 to the negative 4, and this is squared, right? Just because I'm multiplying both by the same number. I'm trying to find the concentration of our hypochlorite. And then I can simply just do this guy here divided by our Kb here to get our hypochlorite. So this here would be ClO minus here would equal, again, I'm doing 1.82 times 10 to the negative 4. And then I'm going to square that. Divided by 3.33 times 10 to the negative 7. And this here will give us our concentration of our hypochlorite ion, which would be 0.0995, which is what they got here, which is great. This is 0.0995 moles. And then finally, what we can do is, given our concentration of this guy here, what we can do is now solve for our our volume, right? So again, we're simply using C1V1 equals C2V2 here, and I'll do this in red. C1V1 equals C2V2. So we know that our C1 here is the concentration of our hypochlorite ion, which is 0.00995, and our volume here is, we wanted, again, 500 milliliters of this solution, right? So we want 500 milliliters of the solution here. So we can say it's 0.5, and then this will equal our C2 here, which was what we got here, right? Our C2 was our concentration here, is what we started with, right? So 0.71, and we want 0.71, and we're solving for our V2 because we were looking at the volume to create this solution here. So the V2 is simply just 0.0995 times 0.5 divided by 0.71. And this here would equal, let me do this, 0.0995 times 0.5 divided by 0.71, and this will give us a value of 0.07 for a V2, 0.070, and this is in liters. And what we want to do is we want to convert this into in milliliters, right, as given. So we're going to multiply this by 1,000. So this here, I'm going to multiply that by 1,000 milliliters over a liter. These two's cancel out, so I have 1, 2, 3. So this here would be 70.0 milliliters. So this here is my solution for this problem here. And again, they got this right as well. So the solution here is correct. Great analysis. Let's see if I can do one last problem before we go here. This is a long question. Again, this is very much probably a university level question or a very, very hard grade 12 question. Just because we are given our density here, we have to somehow find through density, we're given our mass and then our moles and our concentration, and we're given some type of mass percent. So we're taking our grade 11 knowledge and we are extending it to kind of grade 12. You have to write the ionization equation here and also our equilibrium equation here as well. And then from our POH, we have to actually work backwards to solve for a concentration of our hydroxide ion and then figure out our Kb from our Ka value that's given, and then plug it into our equilibrium constant kind of equation to solve for the concentration of hypochlorite. And then given that, then we can use our relationship between concentration and volume to figure out our what volume was needed in the first place here. So this is a very, very actually tough problem to solve. So this probably, I would actually rank this probably as a university question rather than a high school question here. But it's also very, very doable for a high school student as well. Probably more so in a thinking problem. So this here's number 7. Let's look at number 8 here. So it says, which of one of the following molecules has a zero dipole moment? Anyway, I want to explain, right? So I want a non-zero dipole moment, sorry. I'm given 4 compounds, so I'm just going to draw this out here. So I have CO2. So A here is CO2. I'm going to draw out the compound here. And this here is, oh, sorry. I flipped it up. Sorry. That's why it looked weird. I have CO2 here. And as you can see, these dipole moments are going to cancel each other, right? Again, I have partial negative here. This is partial negative here. This here would be a partial positive because, again, I have these lone pairs here, right? I have 1, 2, 3, 4, 1, 2, 3, 4. And again, you're going to see that these dipole moments here are going to cancel out, right? This vector and this vector is going to cancel out. So therefore, I actually have this here is a non-polar molecule. This here is non-polar. So I actually have no dipole moment here. So this here is a zero dipole moment. So right here, zero dipole. And we only have a zero dipole because the elements on both sides here are the same and it cancels out, right? So this here is a zero dipole. I have AlBr3, so I can write Al here in the middle, and then Br3 would be Br, and Br. And again, for this guy here, bromine here is going to basically going to stretch this out, right? Again, I have AlBr here. This is in a trigonal planar geometry here. If you looked at our periodic table, Al here belongs here, and it's actually going to be hybridized, right? Boron here can make 3 bonds. Aluminum here can also make 3 bonds here. And in this case here, this is a trigonal planar geometry according to Vesper. I don't have any lone pairs here. So they basically, in trigonal planar, they basically cancel out the dipole moments here. So this here is also zero dipole. If you need a refresher on Vesper theory, you can always Google a Vesper theory kind of chart here, and I'll show you that Vesper chart. And this will show you basically how it would bond, right? So if I look at let me maximize this for you. If I look at trigonal planar, this here is AX3, right? This here doesn't have a lone pair, right? This aluminum here does not have a lone pair because it's going to hybridize to form, to have 3 bonds created, right? It can hybridize to create a half-filled shell so that 3 orbitals can, 3 bromines can bond to this guy here. So they have no lone pairs here. So this here is also a zero dipole. C here is CO, or C here is MgBr2. MgBr2. MgBr2 has no dipoles because this here is an ionic compound. Very, very simple. Here's an ionic compound, which means it doesn't even have a dipole moment in the first place. Again, when dissociated in water, these two guys are going to form ions. And then D here is Br2. And Br2 here does not have a dipole moment because it's exactly the same, right? These two guys here are the same elements here, and they don't have a dipole moment because a dipole moment is basically a difference in electronegativity, right? So this guy here is also zero dipole. And finally, for E here, I have F bonded Br, and this here, this compound here, I indeed do have a electronegativity difference, right? This fluorine here is going to pull electronegativity away from this bromine here. So there's a net dipole that's going this way. And the reason why is that if I'm looking at my periodic table here, fluorine here is the most electronegative element. And as I go down in the periodic table, it's actually going to decrease in electronegativity due to the increase in atomic radius here. So knowing that, I know that fluorine is going to pull electron density away from this bromine. So therefore, this here creates a dipole moment. So this here is a non-zero dipole moment. And this solution here is correct. So E here is correct, right? So this here is the correct answer. And as you can see, F and Br they have a difference in electronegativity. That's good. AlBr3 is a trigonal planar. So this guy has a zero dipole. CO2 is linear, also has a zero dipole. That's good. Br2 is nonpolar because it's simply just the same element, right? It's not going to have a difference in electronegativity. And MgBr2 is an ionic compound, so it doesn't even have a transfer electron. So the solution here is correct. Good analysis here. So that's going to be all for today. I think I've only went over 8 questions, which is totally fine. We can pick up where we left off probably on Thursday when we're talking about these grade level questions. Again, my name is Joey. I stream basically Monday to Friday. Monday, Wednesdays, and Fridays are basically my math sessions, and then Tuesdays and Thursdays are my chemistry sessions. So you can definitely check me out there. Again, if you like these YouTube videos and these live streams, all these are pre-recorded, or all these are, sorry, not pre-recorded, but these are going to be posted after the live stream on our YouTube channel at youtube.com/OneClass, so you can access them there at any time. Again, my name is Joey. Thank you so much for watching. Stay safe, stay healthy. Have a great day. Take care.